Efficiency is a really important topic because it tells you how effectively your system is taking the energy you give it and putting it to work. So the efficiency of any given stage or system is the useful output divided by the total input. There are some exceptions to the general rule that ENA is always less than or equal to 1. For example, technically speaking, an air conditioning unit can have an efficiency or an ENA of 5, which would be 500% in some cases, but that's because it's taking energy from somewhere else. Your input is used to run a scavenger that pulls heat from the environment and moves it somewhere else. So that's cheating. In this case, for basically all our calculations, this is going to be less than or equal to 1. Energy is going to leak out of our system rather than leak in. So one thing to understand about efficiency is the efficiency of an entire system is the product of the efficiency of all the stages in that system. And a really good way to visualize this is with what's called a Sankey diagram. You don't need to know the name of it, but it's still interesting to know if you want to look it up. Now, if you're looking at a bigger system as a whole, let's say the entire US power grid, and you want to figure out where our energy goes and how much waste occurs, then these little arrows going down, the diversion from the stream of energy, would be your outputs. But for our class, what we assume is we're putting energy in and we have one goal in mind, in which case our diversions are the energy we lose at each stage. They're the losses, they're the inefficiencies. And so as a result, we can figure out if we're given the efficiency and total energy for some of these stages, we can use that energy to fill in the middle. Because look at what's happening here. Everything is conserved. The energy we started with over here translates into the energy that moves to the next stage and the losses that we have. Same goes for this middle and same goes for this end one. Energy is always conserved. And this hopefully should start to explain why when it comes to efficiency, we multiply the values of efficiency together. They're less than 1. And so we're talking about the percentage of the original energy input that actually makes it to our output. So for example, we want to figure out what our total output is, and we found the energy at each stage. I did not walk you through finding the energy at each stage, but that's pretty simple. So we take, this is after our diversion, we'll call this stage 1. We start with energy going in initially through a system with 90% efficiency. So the first stage after a diversion has 90% of the original energy. That gives you 9 joules. The next stage after that, we say that this stage is 90% as well. So that's 90% of the previous stage, which is 90% of the starting stage, or 81% of the total energy we started with. So that's 8.1 joules right there. Now we change things up a little. The efficiency of this final diversion stage is 80%. Usually this will be a conversion, right? Because you're changing from one form to the other or transmitting energy from one place to another, hence the efficiency losses. So let's figure out what the total efficiency is and the total energy. So the total efficiency, a little hard to write this and stare at a phone screen at the same time, equals 0.9 times 0.9 times 0.8. That's 90% for the first stage we encountered, 90% for the second, and 80% for our final stage. So that's 0.81 times 0.8. Here we go. And a total is 65.6%. Now that looks a little surprising because look at how high the efficiencies were everywhere else, and look how low it is at the end. So when I say conversion between stages is wildly inefficient and incurs significant losses, this is what I'm talking about. It's a little surprising to think that we end up with such a small amount, or what looks like such a small percentage, given these high efficiency values. And that really starts to show you the value of just a few percentage points. So we can say the total energy output that we get is our original energy, 10 joules, total equals E naught N total, right? which equals 6.56 joules. And that's how we can find the energy at these different stages. Yeah, the energy that goes in, you have 2 diversions or more, and you're given a set of conditions and you need to figure out what's going on in some intermediate stage. You're going to have to take all this and work backwards. But again, remember the big picture. The big picture view is that you're dealing with a percentage of whatever came before. You're dealing with following the system back upstream.